Okay, hello, welcome to Math 1C. We are on chapter 11. We're going to continue 11.2, page 1. So what we learned so far, review of 11.1, we talked about sequences. A sequence is a function. As a function, f of n equals to a sub n. And the domain of this function is in natural numbers, counting numbers, and usually the range is a subset of real numbers. So we learned that the terms of the sequence are a sub 1, a sub 2, a sub 3, a sub 4, and the general term is a sub n. We took these and we add them all together to create something new that we call a series. So a series is the sum of terms of a sequence. For example, a series that has first term a sub 1 plus second term a sub 2 plus third term a sub 3 plus n term a sub n, and it continues denoted by Greek letter sigma, showing that you are adding some terms of a sub k. K ranges between 1 goes to infinity. This is an example of infinite series. For example, if you have a sub 1 plus a sub 2 plus a sub 3 plus a sub n, this is denoted by the sum sigma a sub k, a sub k. Your lower limit is 1 because the first index is 1 and it stops at index n, so the upper limit is n. Instead of infinity, we have n. Finite series, infinite series. So these are some new functions. Again, we are defining some functions. Very well. For example, take this sequence, let a sub n be defined as sequence n. The terms of this sequence are 1, 2, 3, 4, 5, and so on. Remember that last time we said that since we have a sequence, we can find the limit of the sequence at infinity. Limit of a sub n while n goes to infinity is infinity. So here you have a divergent sequence. So what if I take these elements, these terms of this sequence, and form my series? So a series by adding the terms of this sequence. 1 plus 2 plus 3 plus the rest of them. So here you have sigma n ranges between 1 to infinity. As you expect, if you add all of these numbers together, since n goes to infinity, this sum is going to be a very big number. So since the sum goes to a large number, it is divergent series. Sometimes you have convergent or divergent sequence, and you get a different behavior for your series. Another series for you. I'm taking another sequence, a geometric sequence. So another example for you. We are still on page 1. Still on page 1. Example. Consider geometric sequence. This sequence. 1 over 2 to the n. And you know that the terms of this sequence are like this. 1 over 2 to 0. 1 over 2 to the first. I'm sorry, 1 over 2 to the first. This is the first term and starts from 2 squared. 1 over 2 to the third. And so on. Remember that since the ratio is a half, and a half is between -1 and 1, this sequence has limit equals to 0. So the limit of 1 over 2 to the n, while n goes to infinity, is 1 over infinity, which is 0. So you have a convergent geometric sequence. Now we're taking this sequence and we're adding all of the terms. We're forming a new object, a series. So here you have 1 over 2 plus 1 over 2 squared plus 1 over 2 to the third plus, which is the sum, 1 over 2 to the n, and starts from 1 to infinity. Later on, we're going to show that this sum is equal to 1. Later, we see that the sum of 1 over 2 to the n and starts from 1 to infinity is equal to 1. Remember that for geometric sequence, for example, r to the n, we have 3 different cases. R to the n. If your r is between -1 and 1, then the limit of this sequence is 0. Your sequence is going to be convergent. If r is equal to 1, and if r is greater than 1, r or r less than -1. If r is equal to 1, then this sequence is convergent to 1. If r is greater than 1 or r is less than -1, it doesn't exist. It's infinite. We say that r is the ratio of geometric sequence. The ratio. Like a half to the n. These are examples of geometric sequences. And so on. Let us continue. We're moving on to page 2. So how do we analyze series? For sequences is easy. You just take the limit of a sequence. If it goes to a unique number, you say that, hey, my sequence is convergent. But what about series? For series, it's a little bit more complicated. So let's learn different techniques how to analyze a series. Let us go over a definition. Let the sum, follow the note, a sub I starts from 1 to infinity, be a series. So you have, what's the meaning of that? It means that you had a sequence. It means that we had a sequence like a sub I, and we took the terms a sub 1, a sub 2, a sub 3, and so on. We added all of these together and formed this series. Then we define something that we call partial sums. Partial sums of our series this way. We say that, okay, S sub 1 is equal to the very first term of this series, A sub 1. S sub 2 is A sub 1 plus A sub 2. So this guy is equal to the series A sub I starts from 1 and stops at 1. This is equal to the series A sub I starts from 1 and stops at 2. S sub 3, A sub 1, A sub 2, A sub 3, which is our series, start from 1 to 3. And we continue. S sub n is A sub 1 plus A sub 2 plus A sub n, which is our series, A sub I starts from 1 and stops at n. So, as you can see, S sub 1, S sub 2, S sub 3, S sub 4, up to S sub n, we can continue this process, form a sequence. So, S sub 1, comma, S sub 2, comma, S sub 3, and so on, form a new sequence. Well, we have a sequence. How we can connect these new terms, this new sequence to our series? We say that if the sequence S sub n is convergent, then our series is convergent. The convenient way to define being convergent for this new object that we defined. Okay, this was our definition. We say that if this sequence is convergent, our series is convergent. Okay, let's go over some techniques. Give you some nice formulas to analyze your series, these new objects, these new functions. Perfect. We are still on page 2. So you can call it definition, you can call it theorem. Some books are referring to this as a theorem, some others are referring to this as definition. So let us call it definition. Geometric series. So let R to the n be a geometric sequence. Then the sum of A is just a constant, a number, times R raised to n minus 1, n starts from 1 to infinity, is equal to, let us use the definition of a series, we get A times R to 1 minus 1 plus A times R to 2 minus 1 plus A times R to 3 minus 1 and so on, which is A plus AR plus AR squared plus the rest of them has a formula. It follows this formula. A divided by 1 minus R if R is between -1 and 1. Induction. So base step is, suppose n is equal to 1. If n is equal to 1, we need to show that left-hand side is equal to right-hand side. So your left-hand side is going to be n equals to 1, so you end up with the first term of the series, which is A. Is it equal to the right-hand side? Okay, if n is equal to 1, show you this. So you have A, R raised to n minus 1. This is your series, and starts from 1 to 1. So here, since n is equal to 1, you're left with the very first term, which is A times R raised to n minus 1, 1 minus 1, which is A itself. Now, hypothesis. Let the formula be true for n equals to k. It means that the sum of A R to n minus 1 and starts from 1 to k is equal to let me write this right down for you. A plus AR plus AR raised to k minus 1. Our goal is to show that, we need to show that the sum of A R to n minus 1 and starts from 1 to k plus 1 is equal to A plus AR plus AR to the k. Very well. So you have this part, you have this equality. They are equal to each other. It means that if you take these terms before AR to K, AR to K, we can replace this by this sum. The sum of AR to n minus 1. And n starts from 1 and stops at k. So n starts from 1 and stops at k. So what do we have here? This guy, which is equal to the sum A R to n minus 1 plus the last term A R to k, and starts from 1 to k. This is the last term of this series. If you add this term here, you get the sum A R n minus 1, and starts from 1 to k plus 1. There we go. So now let us write down the partial sum. Sn is equal to A 1 minus r to the n divided by 1 minus. If you take the limit of s of n, n goes to infinity, with the condition that r is between -1 and 1, this is the limit of a 1 minus r to the n divided by 1 minus r, and n goes to infinity. Since n goes to infinity, you know that r to the n is equal to 0. You already know that. So you can get rid of r to the n. So you're left with a divided by 1 minus r, which is the sum of the infinite series. You have your partial sum. If partial sum is convergent, partial sum is Sn, is a sequence. If your partial sum is convergent, you can say that your infinite series is convergent as well. Note that A, R, both of them are constant numbers. A and R are both constants. Now you can apply mathematical induction and prove the formula. Okay, example. So let me write this little thing here for you. So for a geometric sequence, we have r to the n, defined this way. If r is between -1 and 1, the limit is 0. If r is equal to 1, it is 1. And if r is greater than 1 or r less than -1, you say that it doesn't exist, or it's infinite. And for geometric series, we have this. We have the sum of a r2 n minus 1, n starts from 1 to infinity, which is defined as a over 1 minus r, and r is between -1 to 1. And for geometric series, this is infinite series. So you learn that the finite sum, S sub n, is the sum a r n minus 1, the strength of k. This is S of n. K starts at 1 and stops at n. I'm going to use n since I'm using S of n. That's why I changed the index to k. This is equal to a 1 minus r to the n divided by 1 minus. So know the difference between a sequence, infinite series, and finite series, or the partial sum. Again, if the limit of S of n exists, you say that, okay, my series has a limit, and it is convergent. So we're happy here. Perfect. Let's take a look at this example. Question says, find the sum of, you have 5 minus 10 over 3 plus 20 over 9 minus 40 over 27 plus the rest of it. There you go. So it seems like if I make some little algebraic changes, I can form a geometric series. So let us try to make some changes here. What do I mean by that? For example, I want to factor out 5. Let us factor out 5. Because all of of these fractions have factor 5. So 5 outside parentheses, if you factor out 5, you get 1 minus 2/3 plus, if we factor out 5, you get 4/9 minus 8/27 plus 7/6. Very well. This guy is 2/3. This guy is 2/3 squared. This guy is 2/3 to the third, and so on. So I have 5 in front of 1 minus 2/3 plus 2/3 to the second minus 2/3 to the third plus the rest of it. Now somehow I need to get rid of this negative sign, because if you remember our geometric series, everything is plus. A plus AR plus AR squared plus AR to the third, and so on. So what I'm going to do, I'm going to write it this way. 5 times 1 plus, parentheses, negative 2 plus minus 2/3 squared plus minus 2/3 the third plus the rest. Okay, let us compare this one. I have A, parentheses, 1 plus R squared plus R to the third plus the rest. This is a geometric series, and it is equal to A times 1/1 minus R. Note that your R, your ratio, is negative 2/3. Negative 2/3 is between negative 1 and 1, so I'm happy. This is equal to A, my A is 5, times 1/1 plus 2/3. Let's say common denominator, we get 5/3. We can cancel out 5 and 5. The sum converges to 3. So here your conclusion is the series converges to 3. Very well. What's next? Okay, another example for you. We're moving on to page 3. Example. So here you have this series. Analyze this series. 2 raised to 2n. Okay, 3 raised to 1 minus n, and n starts from 1 and goes to infinity. Okay, so I have 2 raised to something, I have 3 raised to something else. My goal is to try to see if I can form this geometric series for this series. So let us try to make some changes to this series. Very well. Okay. So I have 2 raised to 2n. First of all, I have raised to 2 exponents. I have a raised to m times n. What's the meaning of that? It means that it was a to the m raised to the n. So I have series sigma 2 squared raised to n times 3 to 1, 3 to negative n. Very well. And n starts from 1 and it goes to infinity. So this is equal to the series 4 to the n. 2 squared is 4, and I have 3 to the first power times 1 over 3 to the n. So let me just write this with a different color so you know what I did. So it's 2 squared. I have 2 raised to 2n, 2n. So I have 2 raised to 2, all raised to n. So I have 4 to the n, 3 to the first power, 1 over 3 to the n. Excellent. Now I can combine these two. And 1 to infinity. This is the sum. 4/3 to the n. 4/3 to the n. Very good. I'm trying to form a r raised to something. And I have 3 to the first power. N starts from 1 and it continues to infinity. Remember that you need exponent k minus 1. So if I write it this way, I only see exponent n. I don't see n minus 1. What can I do? I can keep this guy as, let's see, 1 minus n. Then I can flip this guy down here. I can create 3 raised to n minus 1. So let us do this. So let us write this like this way. 4 to the n times 1 over 3 raised to n times 3 to negative exponent n minus 1. What about this guy here? I have 4 to the n. So if I multiply this by 4 to negative 1, divided by 4 to negative 1, then I'm done. This guy can be written as the sum 4 to n minus 1 times 4. Let me write the 4 here for you. Then the whole thing is divided by 3 raised to n minus 1. And n starts from 1 and it continues to infinity. So this guy is now my geometric series. I can write this 4 outside the series. And I have the sum 4/3 raised to n minus 1 and starts from 1 to infinity. This is very similar to what I have as a geometric series. So know that your ratio R is 4/3. 4/3 is greater than 1. So we have a divergent series. Perfect. Next example. So we are still on page 3. Okay. We have this example. This example says, write the decimal number 2.3171717. So 17 is repeated, or 2.317. Remember that we put a little bar on top of 17 to show that 17 is repeating here as a ratio of integers. Ratio of integers. Okay, let us break this number down to see what do we have here. So we can rewrite this decimal number as follows. We have 2.3171717, the rest of them. So this is actually the sum of 2.3 plus 0.017 plus 0.00017 plus the rest of it. this number is the sum of 2.3 plus 0.017 plus 0.00017 and so on. Okay, here you have 2.3 plus 17 over 1,000 plus 17 over 1, 2, 3, 4, 10,000 plus the rest. Okay, so here you have 2.3 plus 17 divided by 10 to the 10 plus 17 over 10 to the 4 plus the rest of the things. So what I'm going to do, I'm going to factor out 17 divided by 10 to the 3rd. I get 2.3. So you rewrite this one here and make more space. This is 2.3 plus 17 over 10 to the 3rd plus 17 over 10 to the 4th plus the rest. So here I have 2.3 plus 17 divided by 10 to the 3rd, 1 plus 1 over 10 plus the rest. This line has 5 zeros. 1, 2, 3, 4, 5. It's not 4, but it's 100,000. Guys, this picks up. Here you have 10 to the. Here you get 10 squared. Very good. So this part is similar to our geometry series. This is your A, and you have 1 plus R plus R squared plus the rest. So this sum is equal to 2.3 plus 17 over 1,000 times 1 over 1 minus R. What is R? R is 1 over 100. And as you can see, it is between -1 and 1. So we have a convergent sequence. A convergent sequence, I mean S of n. So you'll get a convergent series. So this is equal to 1 over 100. If you simplify this side, let's see. You get 2.3 plus 17 over 1,000 times, you get 100 divided by 99. You can cancel out zeros and zeros here. So here you get 223 divided by 10. Or let us write it in decimal form, 2.3 plus 17 over 99. And it has another 0, okay, which is equal to, so the sum 1147 divided by 495. Another example for you. We are on page 4 of the note. Example. So this example says find the sum of the series sigma x to the n, and starts from 0 to infinity, and your absolute value of x is less than 1. What's the meaning of that? It means that x is between -1 and 1. Okay, perfect. So if you rewrite this series, it is x to the 0 plus x to the first plus x to the second plus x to the third and so on. And since x is between -1 and 1, we're not actually worried about the ratio here. It means that the ratio is between -1 and 1. So this is 1 plus x to the first, x squared plus the rest of it. If you compare this with geometric series, then it means that it is equal to a, the first term, 1 divided by 1 minus x. This is your sum. Another example for you. So this example says, show that the series 1 over n times n plus 1, n starts from 1, goes to infinity, is actually a convergent, is actually a convergent series. Very good. So let us try to simplify this series, write down some terms, see what we're dealing with. So let us simplify this series, then write some terms down. First of all, this is a fraction that you can use decomposition of fractions and rewrite this. You have 1 over n times n plus 1. This is a over n plus b over n plus 1. Decomposition of fractions. So it means that a times n plus 1 plus b times n is equal to 1. So an plus a plus bn is equal to 0 times n plus 1. So if you factor out n, you get a plus b plus constant a equals to 0 times n plus 1. So what's the meaning of that? It means that a plus b is equal to 0 and a is equal to 1. So a plus b is equal to 0 and a is equal to 1. So b is equal to minus. So this series can be written as the sum 1 over n, n plus 1, n starts from 1 to infinity as the sum 1 over n minus 1 over n plus 1, n starts from 1 to infinity, by using the decomposition of fractions. Now, write some terms down. S of n, partial sums, is equal. If you plug in 1, you get 1 over 1 minus 1 over 1 plus 1, which is 2, plus the second term, 1 over 2 minus 1 over 2 plus 1, plus the third term, 1 over 3 minus 1 over 3 plus 1 plus the rest of them. Okay. Take a look at this. S of n is 1 plus minus a half plus a half minus a third plus a third minus a fourth plus a fourth plus. So since it is S of n, we get minus 1 over n plus 1 over n minus 1 over n plus 1. So as you can see, you have opposite numbers. A half, negative a half. A third, negative a third. A fourth, negative a fourth. 1 over n, negative 1 over n. What's left? This sum, this partial sum Sn is 1 minus 1 over n plus 1. And we all know that if this limit, the limit of Sn exists, we say that your series is convergent. So since the limit of 1 minus 1 over n plus 1, while n goes to infinity, is 1 minus 1 over infinity, 1 minus 0 equals to 1, it means that our series is a convergent series. So our series sigma 1 over n, n plus 1, n starts from 1 to infinity, converges to 1. Very well, let us continue. Harmonic series. You are on page 5 of the notes. Page 5, example, harmonic series. Which is defined as series 1 over n, and starts from 1 and goes to infinity. Okay, let us analyze this series first. Remember that, recall that sequence 1 over n is defined this way. If you plug in 1, you get 1 over 1 to 1. If you plug in 2, you get 1 over 2. If you plug in 3, 1 over 3, 1 over 4, and so on. If you remember the graph of this sequence, but it's not a series, just a sequence. So at 1, you have 1, first point, a sub 1. Then at 2, you have a half. At 3, you have a third, a sub 3. And at 4, you have a fourth. And if you remember, the limit of 1 over n, while n goes to infinity, is 1 over infinity or 0. So this sequence is a convergent sequence. This example is very important. This sequence, again, sequence is convergent. What we're doing, you're taking the elements, the terms of this sequence, add them all together to form this new object, harmonic series. Very well. Let's take a look at the terms. This is 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 and so on. Let's take a look at partial sums. Partial sums. S sub 1 is 1 over 1 or 1. S sub 2, okay, 1 plus a half, which is 3 halves. S sub 3 is 3 halves, S2 plus a third. If you take common denominator between these two, it's going to be 6. 6 and 11 over 6. Okay, take a look at this. S4 is 11 over 6. plus 1 over 4. You get 44 plus 6, which is 50 over 24. You can simplify this as well. You get, if you divide it by 2, you get 25 divided by 12. Then you can form S sub 5. We are forming partial sums. Then we look at the behavior of this sequence, of this new sequence. It is 25 over 12 plus 1 over 5. So if you take common denominator between these two, you get 60. Then here 5, 125 plus 12, which gives you, let's see, 137 over 60, and it continues. Unfortunately, this sequence is a divergent sequence. So, harmonic series is divergent. So if the question, if the exam says, give us example of a convergent sequence with divergent series, harmonic series is that example. So this is not a geometric series. This is not a geometric series. For geometric series, we have ratio raised to n minus 1. It is multiplied by a constant. A times 6. 1, 2. So you must see an exponent. You don't have that exponent as the variable here. Okay, what's next? We have a theorem here. We are on page 6. We have a very nice theorem. Theorem on page 6. This theorem says if series like sigma an and starts from 1 to infinity is a convergent series. If series is convergent, then for sure the limit of the general term while n goes to infinity is equal to 0. So I expect you to ask, if the limit of the general term is equal to 0, can I conclude the series is convergent? Question. Is the inverse of this theorem true? It means that if the limit of the general term while n goes to infinity is equal to 0, then can I conclude that my series is convergent? The answer is no. No. Because we have a counterexample. What is that example? Harmonic series. Harmonic series. Harmonic series, series 1 over n starts from 1, goes to infinity. An, general term, is 1 over n. The limit of 1 over n while n goes to infinity is equal to 0, but we saw that the series is divergent. So the inverse is not true. Conclusion. The contrapositive of this theorem is, let us write it as a note, if the limit of an while n goes to infinity is not equal to 0, or the limit of an while n goes to infinity gives you two different numbers, gives you infinity, so in general does not exist, then for sure you can say that the series an while n starts from 1 to infinity is divergent. There you go. Perfect. Example. So example says, we're still on page 6. Example says, show that the series n squared over 5 n squared plus 4 diverges. Very well. Let us take the limit of an. If the limit is not 0 or doesn't exist, for sure I can say that the series is divergent. So let us find the limit of an. If this limit is not equal to 0 or does not exist, then we can conclude that our series is divergent. So limit of an is n squared divided by 5 n squared plus 4, and n goes to infinity. Remember that since n goes to infinity, you can ignore lower terms. 4 is not important. N goes to infinity much faster than 4, so you can ignore 4. This is the limit of n squared over 5n squared. N goes to infinity. We can cancel out n squared and n squared. We get 1 over 5. Of course, 1 over 5 is not 0. So the series n squared over 5 n squared plus 4 diverges. Okay. Next page, another example for you. We are on page 7. So here you have this series. The sum of 3 divided by n plus 1, plus 1 over 2 to the n starts from 1 and goes to infinity. Perfect. So here you have an. Let us take the limit of this an to make sure that it's not non-zero or doesn't exist. So let us check the limit of an. A sub n while n goes to infinity. This is the limit of 3 over n n plus 1 plus 1 over 2 to the n, while n goes to infinity. So here you have 3 over infinity plus 1 over infinity, which is 0 plus 0 or 0. Okay, we're good so far. Now for the series itself. For the series. For the first part, here you have a telescopic series, and for the second part, you have a geometric series. S of n can be written as the sum 1 over k minus 1 over k plus 1 multiplied by 3. K starts from 1 and starts at n. I'm finding the partial sum plus sum 1 over 2 to the k. K starts from 1 to n. There we go. I know that this guy is like this. This is S of n is 3, 1 over 1 plus 1 over 2 minus 1 over 2 plus 1 over 2 minus 1 over 3 plus 1 over 3 minus plus 1 over. So let me just write down the last term. You already know how to decompose this. Plus the sum, a half to the k. K starts from 1 to infinity. So here I know that I can cancel out a half, negative a half, a third, negative a third, and the rest of the terms. So S of n is 3 times 1 minus 1 over k plus 1. And this is just a geometric series. Here I get plus a half, plus a fourth, plus 1 over 8, plus 1 over 2 to the 10. And here the last term is n plus 1. Okay, make sure everything is correct. So if you take the limit, this is 3, 1 minus 1 over infinity, the limit of Sn, while n goes to infinity, and this guy is equal to just 1. So you get 3 times 1 minus 0 plus 1, or 3 plus 1, or 4. Add this here. This is the sum of 1 over 2 to the k. K starts from 1 to. So this is your geometric series. The limit of series, a half to the k. K starts from n, while n goes to infinity, is equal to a, which is a half, divided by 1 minus r, 1 minus a half, which is a half, divided by a half, which is here. This one here is coming from this geometric series. Very well, let's see what's left. Okay, one more example, then we're going to finish 11.2.
There's a question, Professor.
Okay, our last example on 11.2. page 8. Example. So what do we have here? We have, okay, finite terms of, analyze this series. N divided by N cubed plus 1, and starts from 1 and goes to infinity. First, we find the limit of the general term. So first, find the limit of an while n goes to infinity. Note that if the limit of n goes to infinity is not 0 or doesn't exist, we say that series is divergent. So the limit of n over n cubed plus 1 while n goes to infinity. Since the degree of the numerator is less than the degree of the denominator, this is 0. So we have. Now we try to analyze our series itself. So let us form the partial sums. S sub 1 is 1 divided by 1 plus 1, or a half. S sub 2 is a half plus 2 divided by 8 plus 1, or a half plus 2 over 9. We get 9 plus 4, which is 13 over 9. Okay, I had a half, now I have 13 over 9. It seems like it is increasing. Let's find the rest of the terms. S sub 3 is 13 over 9 plus, now if you plug in 3, you get 3 over 28. So if you take common denominator between these two, okay, let's see. $252, and if you multiply these two, 13, 28, 364 plus 27. Okay, here you have 395 over 252. Okay, it's not that bad. It seems like you're just staying around one number. S sub 4 is 391 divided by 252 plus, let's plug in 4 divided by 65. If I take common denominator between these two, I get 65 times 252. And on the numerator, I have to multiply these two, 391 times 65 plus 4 times 252. And after doing the algebra, thanks to you, it is 1.61. It seems like this series is a convergent series. This is a convergent series. Later on in 11.3 through 11.8, we're going to go over techniques to actually compare this series with other convergent series and actually make a strong conclusion about series.